Hey friends, welcome back. AI Gateway, Inference Tables, Cost Control, and SME feedback loops is one of those topics where a single qualifier word changes the answer. Today we'll see exactly why. Let's get into it. Here's a silent failure mode most teams discover the hard way. Your inference table has a 1 MB payload cap, and anything larger disappears without a trace. No error, no row, just gone. By the end of this video, you'll know how to catch that, and everything else a SOC 2 reviewer will ask for. The audit log, the per-tenant chargeback, the rate limits, the guardrails, and the expert calibrated evaluators. We'll also clear up the most common confusion in this space. Inference tables and MLflow tracing are not the same thing, and the difference shapes how you design observability. One sentence of context before we go. Episode 12 got us to a deployed endpoint. Episode 18 taught us how to evaluate it. Today is the production layer that wraps both, so an enterprise client will actually sign the contract. 5 terms will show up throughout the rest of this video. Let's pin them down now so they land in context later. An AI Gateway Inference Table is the Unity Catalog Delta table that logs every request and response. Usage_context is the optional map you attach to a request so you can answer questions like, how many tokens did tenant A burn this month? QPM and TPM are the 2 rate limit units, queries per minute and tokens per minute. The inference log profile is the Lakehouse monitoring mode that sits on top of an inference table and computes drift over rolling windows. And the guidelines judge is an MLflow scorer that evaluates output against a plain language rubric. That's how we scale expert judgment without replacing the experts. Datadino just landed a Fortune 500 natural history client, and the contract came with a follow-up. The client is SOC 2 audited, and they want 4 things in writing. Per-tenant latency numbers, broken down by which museum is hitting the chatbot. Toxicity scores on every single response. Drift alerts that fire before quality degrades, not after, and all of it has to be auditable, meaning not a screenshot in a slide deck, but a queryable record an auditor can run SQL against. Datadino's deployment from episode 12 does none of these things today. So the question becomes, where do those numbers actually live? Every one of those answers, the per-tenant cost, the toxicity score, the drift alert, the audit log, comes from the same Databricks control plane. AI Gateway, it's the layer that sits between your client app and your model-serving endpoint, and it's where observability, governance, rate limits, guardrails, and cost levers all converge. If you only remember one thing from this video, remember that AI Gateway is the answer to the SOC 2 scenario. Picture AI Gateway as a toll booth on the highway between your client app and your model-serving endpoint. Every car, every request, has to stop at the booth. The booth checks ID, which is the requester column. It collects a toll, which is the token count. It scans for contraband, which is the guardrail layer for PII and unsafe content. It enforces a lane limit, which is the queries per minute and tokens per minute rate limit. And the booth keeps a ledger of every car that passed through, which becomes your inference table and your usage table. 1 booth, 5 jobs. That's why AI Gateway is described as a single control plane. Let's start with the ledger. An AI Gateway Inference Table is a Unity Catalog Delta table that automatically logs every request and every response your serving endpoint sees. You enable it per endpoint in the AI Gateway configuration, no code change in the client, no SDK update, nothing. Because it's a Delta table under Unity Catalog, it's durable, it's queryable in SQL, and you can join it to other governed tables. Every monitor we build later in this video and every chargeback dashboard sits on top of this one table. This is the audit log a SOC 2 reviewer asks for. Here's the schema you should be able to recognize. Databricks_request_i.d is the unique server issued ID for the call. Client_request_i.d is what the caller supplied, which lets you correlate to your own application logs. Requester tells you which user or service principal made the call. Status_code is the standard HTTP code 200, 400, 429, 500. Request_time and execution duration in milliseconds give you when and how long. Then you've got the raw request and response payloads, capped at 1 MB. We'll come back to that limit. For foundation model endpoints, you also get input and output token counts. Served_entity_i.d is the join key to the served entities table. Usage_context, in green, is your tenant attribution map, and logging_error_codes, in orange, is how you find out the row didn't capture what you expected. Of every column on that schema, usage_context is the one to design in from day one. It's an optional map you attach to the request body. Keys like project, end_user_to_charge, and a_b_test_group are typical. It's capped at 10 kibibytes, so keep it small. And without it, you genuinely cannot answer the question, how many tokens did tenant A burn this month? The killer is that bolting it on after launch means changing every client SDK that calls the endpoint. Set it on day one. Now the caveat to no cold, straight from the Databricks docs, the maximum request, response, and trace size that are logged is 1 MB. Payloads that exceed this are logged as null, and logging_error_codes are populated with max_request_size_e_exceeded, or the matching response code. That's a real limit. If a payload is over a megabyte, the row still lands, but the request and response come back null. In practice, this catches 3 kinds of workloads: long PDF payloads pasted into a prompt, base64 encoded images going into a multimodal endpoint, and huge agent traces with many tool calls. All 3 can silently disappear from the audit log. The wrong mental model is, no row in the table means no traffic. The right move is to filter on logging_error_codes in every monitoring query so you can see the rows that landed empty. And the upstream fix is to chunk, summarize, or pass references in the request body rather than the payload itself. Now the misconception this video exists to fix. Inference tables and MLflow tracing are not the same thing. They are 2 different lenses on the same call. Inference tables, on the left, capture the endpoint level payload, 1 row per call, queryable with SQL, joinable to your billing tables. Think of them as the security camera at the front door of the building. Every entry and exit, time-stamped, durable. MLflow tracing, on the right, captures the hierarchical spans of what happened inside the call, walking through the retrieval step, the tool calls, and the generation. Those spans are open telemetry compatible objects, not delta rows. That's the body cam on the security guard walking the halls. Same call, different evidence. The reason this matters in practice is that they answer different questions. You cannot debug an agent's tool call loop from a single payload row in a delta table. The row tells you what came in and what came out, but not which tool fired in what order. And you cannot bill a tenant from a span tree. The spans are great for debugging, but they're not the durable, joinable substrate billing needs. The right design uses both, for different jobs. Quick pivot before the next block. We've got the toll booth and the payload log, the durable record at the door. We've also established that tracing is a different lens, spans inside the call, not the payload at the door. What we don't have yet is the chargeback dimension and the circuit breaker that stops one tenant from drowning out the others. That's next. Databricks ships 2 system tables that you join together for chargeback. Start with system.serving.served_entities. That's the lookup dimension, 1 row per model and version, with the model name, the endpoint, and the creator. Then system.serving.endpoint_usage has one row per request, with input and output token counts, the status, and the usage_context map. You join them on served_entity_i.d to turn an opaque hashed ID into a human-readable model name. One thing to plan for though, both tables are account admin only by design. If you want a workspace engineer to build a chargeback dashboard, an account admin has to either grant access or materialize a curated view. Here's the join in its simplest form. We pull end_user_to_charge out of the usage_context map. That's the tenant key data deno set on every client request. We join endpoint_usage to served_entities on served_entity_i.d, which gives us the model name instead of an opaque hash. We sum input and output tokens, count the requests, and group by tenant and model. Run this over the last 30 days and you've got the per-tenant breakdown the Fortune 500 client asked for. The thing to notice is that the tenant key is just a dictionary lookup into usage_context, which is why setting that field on day one matters so much. Rate limits are your circuit breaker for cost blowouts and noisy neighbor protection between tenants. AI Gateway gives you 2 units. Queries per minute, QPM, counts whole requests. Tokens per minute, TPM, counts the tokens inside them. You scope each limit to one of 5 things. The endpoint scope sets a global cap across all traffic. The default user scope applies to every user who doesn't have a specific rule. A specific user scope is an individual override for one named user. And then you have service principal and user group for machine identities and team level caps. The renewal period is always per minute, and there's a hard cap of 20 rate limit entries per endpoint. So you can't define 1,000 per tenant rules. You'll group most tenants and only carve out exceptions. Straight from the docs, you can specify a maximum of 20 rate limits per endpoint. Rate limits apply only to users with permission to query the endpoint. 20 is the number to remember. And note the second sentence, a rate limit is not an authorization mechanism. If a caller doesn't have permission to hit the endpoint at all, the rate limit is irrelevant for them. Limits are about shaping the traffic of people who are already allowed in. Here's how the scopes layer together. At the top is the endpoint ceiling, a global cap that applies to everyone regardless of identity. Below that, an individual user or service principal limit overrides whatever the group default would have been, and the group limit is the default that applies when no individual rule fires. Think of it like a nightclub. The fire marshal capacity for the whole building is the endpoint ceiling. Nobody else gets in once you hit it. The bouncer's clipboard is the user-level rule, and your individual quota always wins over the group default. Then on the bottom, QPM versus TPM. If both are set on the same scope, the more restrictive of the two is enforced. So if your QPM allows the call but your TPM is already exhausted for the minute, the TPM wins and you get rate limited. Now here's the limitation that matters for production capacity planning. TPM only works where the platform natively counts tokens. That's the foundation model APIs and external models proxied through the gateway. On a custom model endpoint or an agent endpoint, the platform doesn't have a native token count to enforce against. So if you set a TPM on a custom model endpoint and expect it to throttle, it won't behave the way you think. For custom models and agents, capacity planning is request rate math, QPM and the underlying concurrency settings, not token budget math. Here's the precision point on rate limits that catches teams off guard. Enforcement is intentionally eventually consistent. The limiter checks usage after responses are sent, not before, which means brief bursts above your configured cap are normal, especially right after you create or update an endpoint. Overlimit calls return HTTP 429. The mental model is, treat the cap as a guardrail against runaway spend, not as a hard ceiling for tight latency SLAs. If you need a true hard cap, you build it at the application layer in front of the gateway. Now, the sunset. Databricks is retiring the legacy inference tables experience, and the migration is a one-way door. From the docs, after an endpoint migrates to use an AI Gateway Inference Table, it cannot switch back to the legacy table. The schemas are different, which means any downstream dashboard or query you built on the legacy schema has to be rewritten before you flip the switch. Here's the timeline. Today, you can have legacy tables on some endpoints and AI gateway tables on others. They coexist. On February 20th, 2026, you can no longer enable the legacy experience on any new or existing endpoint. On April 30th, 2026, the legacy inference table experience is fully unsupported. After that, only AI gateway-enabled tables remain. Rebuild downstream dashboards against the new schema. So for any new deployment you're shipping today, the answer is the AI gateway-enabled table. That's the migration picture. AI gateway tables are the path forward, and the April 2026 sunset is the forcing function. Now to the part of the system that decides whether this whole architecture stays affordable: cost levers, then monitoring profiles, guardrails, and the SME feedback loop. There are 5 cost levers worth knowing, and they go in this priority order. First, rate limits. They stop runaway spend at the door before it ever reaches the model. Second, smaller models for high-volume tasks. Datadino routes 100,000 support tickets a day through an 8 billion parameter instruct model. There's no reason to pay 70 billion prices for queue routing. Third, match the serving modality to the traffic shape. Pay per token versus provisioned throughput. Fourth, AI_query for batch, the cheapest path for any offline workload. And fifth, prompt caching, which is automatic, free, and compounds with batching. The decision rule is, match the modality to the traffic shape. Pay per token is like Uber, perfect for sporadic, low-volume traffic. Provisioned throughput is like leasing a car, a fixed monthly bill that pays off when you drive every day, so steady 24/7 workloads with latency SLAs. And AI_query batch is the bus, the cheapest way to move 100 people overnight, meaning offline scoring over a delta table. On the right are the common mismatches. Provisioning throughput for a once-a-day batch job means paying 24 hours of compute for 1 hour of work. Pay per token for a steady production agent loses the volume discount. And the most expensive mistake, a Python loop calling a foundation model endpoint row by row instead of using AI_query. That single mistake can 10 times your bill. Then there's the lever you don't have to pull. Prompt caches on the platform are implicit, isolated, and stored only in volatile memory. They're never persisted to disk, and you never configure them. That answers 2 scenarios in one sentence. Is it safe? And do I have to turn it on? The answer to both is, the platform handles it. And the numbers are real. In Databricks' own reported benchmarks on open-source foundation models, prompt caching delivered 2.5 times the throughput and 3 times faster P50 latency. The configuration required on your side is 0. The way it works is the pre-fill stage, reprocessing the system prompt, gets skipped on a cache hit. If your system prompt is long and your user message is short, which is most RAG and agent workloads, the savings compound dramatically. Lakehouse monitoring offers 3 profile types. Snapshot computes point-in-time stats over a whole table, capped at 4 terabytes, no time windows, no drift. Time series computes windowed stats over a timestamp column, with a default 30-day metric window. But for a serving endpoint, the profile you want is inference log. That one adds model quality, fairness, and drift on top of windowed stats. It sits directly on top of an AI gateway inference table. When you want graded quality, you give it a label column, a prediction column, and a model ID column. And critically, it compares each window against a baseline reference table, so you can detect when this week's traffic drifts away from your training distribution. The rule is simple. If you have a serving endpoint and you care about drift versus a baseline, inference log is the only profile that applies. The other two are for general delta tables. Here's what an inference log monitor actually emits. You start with the AI Gateway Inference Table. That's the delta table on the left. You attach an inference log monitor to it. The monitor produces three things automatically: a profile metrics table, holding per window summary stats like means, quantiles, and counts, a drift metrics table, holding both window-over-window comparisons and comparisons against your baseline reference, and an auto-generated DBSQL dashboard that visualizes both. The dashboard is what you hand to the SOC 2 auditor. The metric tables are what you alert on with DBSQL alerts that fire workflows when thresholds break. The dashboard is a DBSQL dashboard that queries the metric tables, so hitting refresh on the dashboard doesn't recompute drift, it just rereads whatever's already sitting in the metric tables. To get fresh numbers, you have to refresh the monitor first, which is what actually triggers the windowed computation. Then refresh the dashboard. The order matters, and it's the kind of thing that's easy to miss the first time you wire this up. Now to that toxicity score the SOC 2 client wanted in writing. That's the AI Gateway Guardrails layer, which we covered the threat side of in episode 16. The guardrails cover PII, unsafe content, jailbreak attempts, and hallucination signals. 2 enforcement modes: block returns HTTP 400 and stops the request. Sanitize redacts in place and lets the call proceed. Here's the part most people miss about the audit trail. Output blocked and sanitized requests do land in the inference table, but input blocked requests, where the guardrail fires on the prompt before the model ever runs, those are absent from the inference table entirely. They show up in the usage tracking table, system.serving.endpoint_usage, with status 400 tokens. So your auditable record spans 2 tables, not 1. Configuration lives on the endpoint, not in your application code, which means a security team can tune policy without an app deploy. Last block, the subject matter expert loop that turns episode 18's evaluation harness into something you can run continuously in production. The built-in scorers from episode 18 handle retrieval relevance and groundedness, generic things any RAG app cares about. But domain quality, the stuff the Fortune 500 paleontology client actually pays for, needs domain experts. And here's the constraint: you have maybe 3 SMS. You have 10,000 traces a night. The math doesn't work. So the pattern is 3 stages. Experts define a rubric. You calibrate raters against each other until inter-rater agreement is solid. Then you hand that calibrated rubric to an LLM judge, which runs at scale. We'll see exactly how that flows next. The loop has 5 steps. First, your SMS define the rubric in plain language. Things like, cites a source PDF, uses neutral tone, escalates when uncertain. Second, pick 20 to 30 edge cases from production traffic, not easy ones, the hard ones. Third, calibrate. 2 or more SMS grade those examples independently, then sit together and resolve disagreement. The disagreement itself is the signal that tells you where the rubric is ambiguous. Fourth, use the aligned labels to tune a guidelines judge or a custom scorer so its verdicts match the experts. Fifth, pass that calibrated judge to MLflow.GenAI.evaluate and run it against nightly traces. The calibrated judge can then grade thousands of traces consistently, while your experts focus on the genuinely hard cases. Here's how it wires together in code. Make_judge constructs a custom LLM judge from a natural language prompt. That's where the calibrated rubric goes. Datadino's curator rubric scores 1 through 5 on 4 criteria, cites a source PDF, neutral tone, flags uncertainty, and no fabricated extinction dates. That last one ties straight back to the investor demo hallucination from episode 16. Then in the evaluate call, the judge sits alongside the built-in retrieval groundedness and relevance to query scorers. The pattern that matters is the comment on the last line. The calibrated judge is not a replacement for the curators, it's the scale layer on top of their judgment. And the misconception to drop is the one that ruins evaluation programs. An uncalibrated LLM judge optimizes your model toward the wrong target. If you wire up a generic LLM judge with a vague prompt and start tuning your retrieval pipeline against its scores, you'll improve a number that doesn't correlate with what your domain experts actually care about. The experts define the rubric. The experts calibrate the judge. The judge then scales the judgment across thousands of traces. That order is the difference between an evaluation program that converges and one that drifts. 5 decision rules to walk away with. Audit log requirement. AI Gateway Inference Table. Since legacy sunsets April 30, 2026. Per-tenant cost attribution. Usage_context flowing into system.serving.endpoint_usage. Capacity planning for a custom model or agent endpoint, QPM, not TPM. Drift detection on a serving endpoint, an inference log monitor on the inference table, and scaling SME judgment across nightly traces. Calibrate a guidelines judge on 20 to 30 edge cases, then pass it to MLflow.GenAI.evaluate. Back to where we started. Datadino can now hand the SOC 2 auditor the inference table for the audit trail, the toxicity guardrail log for every response, the inference log drift dashboard, and the per-tenant chargeback SQL, all from one control plane. So 5 things to remember. AI Gateway is the one control plane for observability, governance, rate limits, guardrails, and cost. Inference tables log payloads. MLflow Tracing log spans, same call, different lens, cost levers in order, rate limits, smaller models, modality match, AI_query for batch, and automatic prompt caching. Inference log profiles turn an inference table into drift alerts with an auto-generated dashboard. And the rule that closes everything, SMS define the rubric, LLM judges scale it, never the other way around. Now let's see how well all of that landed with a quick 5-question quiz. Alright, let's test what you've learned. Question 1. A SOC 2 audited client asks Datadino for a queryable record of every request to the museum chatbot, including the requester, status code, end-to-end latency, and raw payloads. Which Databricks capability provides this directly, with no application code change? Is it A, MLflow tracing on the predict method of the responses agent, B, an AI gateway-enabled inference table on the serving endpoint, C, a custom logging callback wired into the LangChain chain, or D, the system.billing.usage table filtered by serverless real-time inference? Take a moment to think about it. The answer is B. AI gateway-enabled inference tables write every request and response straight to a Unity Catalog Delta table, with the requester, status code, latency, and payloads all included, and you turn it on per endpoint without touching application code. MLflow tracing logs the spans inside the call, not the audit-grade payload at the door, and the billing table tells you what something cost, not what was said. Question 2. Datadino's production custom model agent endpoint serves a steady 200 requests per minute. The team configures a TPM rate limit of 500,000 tokens per minute to cap spend. During a traffic spike, the endpoint never throttles even after exceeding 500,000 tokens. Why? Is it A, TPM enforcement is eventually consistent and ignores spikes under 1 minute? B, TPM rate limits do not apply to custom model or agent endpoints. Token semantics are native only to foundation model APIs. C, the team forgot to set the renewal_period, the default is per hour. Or D, TPM is only enforced once QPM limits are also set on the same endpoint. Take a moment. The answer is B. Token per minute limits depend on the platform natively counting tokens, which it does for foundation model APIs and external models. On a custom model endpoint or an agent endpoint, the platform doesn't have native token semantics to throttle against. So for capacity planning on those endpoints, you use QPM and the underlying concurrency settings. Question 3. Datadino runs a nightly classification job over 50 million support tickets in a Delta table. The team currently uses a Python for loop that calls a pay-per-token foundation model endpoint row by row. Which change provides the largest cost reduction without changing the model or accuracy? Is it A. Switch from pay-per-token to provision throughput for the duration of the nightly job? B. Increase the QPM rate limit on the endpoint to allow higher parallelism in the loop? C. Replace the Python loop with a I_query invoked from SQL over the Delta table? Or D. Enable MLflow Tracing on the endpoint to capture per-row latency and parallelize after analysis? Take a moment. The answer is C. AI_query is the canonical Databricks pattern for batch inference. It automatically parallelizes, retries, and scales across the Delta table in one SQL query, and prompt caching reuses repeated system prompt prefixes across all 50 million rows for free. The Python loop bypasses all of that and pays the per-token rate serially. Provisioned throughput could help, but it's the wrong modality for a once-a-day job, and you'd be paying for idle compute the other 23 hours. Question 4. Datadino's ML lead wants drift alerts when this week's request distribution diverges from the training baseline on the fossil chatbot endpoint. Which Lakehouse monitoring configuration is correct? Is it A. A snapshot profile on the inference table, refreshed nightly? B. A time series profile on the inference table, comparing each window to the prior window? C. An inference log profile on the AI Gateway Inference Table, with a baseline reference table set to the training distribution? Or D. A custom Delta production tables pipeline that recomputes KL divergence between request_time windows? Take a moment. The answer is C. The inference log profile is the right tool for a serving endpoint. It sits on top of the AI Gateway Inference Table, computes windowed stats, and crucially supports a baseline reference, which is what gives you drift versus training rather than just drift versus last week. Snapshot has no windows at all. Time series has windows but no baseline-driven drift. And rolling your own pipeline reinvents what inference log gives you for free, along with the auto-generated dashboard. Question 5. Here is a scenario. A fossil chatbot evil run returned the following scores: retrieval groundedness, 94%, retrieval relevance, 89%, retrieval sufficiency, 76%, correctness, 81%. Which interpretation is correct? Is it A. The generator is hallucinating, retrieval groundedness needs to be raised before correctness can improve? B. Retrieval is finding relevant documents but not enough of them to fully answer the question, increase top K or improve recall? C. The judge is uncalibrated, rerun with a guidelines judge tuned on 20 to 30 SME labeled edge cases? Or D. The vector index is stale, enable continuous sync on the delta sync index? Take a moment. The answer is B. The signal is in the gap between the four scores. Retrieval groundedness at 94% says the generator is staying faithful to what it was given. Retrieval relevance at 89% says most of what it retrieves is on topic. But retrieval sufficiency at 76% says the retrieved set often lacks enough material to fully answer the question. That's a recall problem, not a generator problem. The fix is to widen retrieval, raise top K, add hybrid search, or apply query expansion, not to retrain the model. Alright, that's AI Gateway, Inference Tables, cost control, and SME feedback loops in the bag. Subscribe for the next episode of the Databricks GenAI Engineer Cert. Give the video a like if it helped, and I'll see you in the next lesson.